This is part 4 of the AQA A-level chemistry topic amount of substance. In this one, we're going to look at reacting masses questions. So another big and very important calculation. I'm going to recommend that you pause as you're going through and try each question. And then you can review and see how successfully it's gone and potentially what you might need to go back and revisit. So in the first instance, we're looking at balancing equations. So we're going back to GCSE standard really, but it's good to just rethink it. Think carefully about the questions here. When you've had a chance, have a look at the answers. So we're starting off with the difference between word and symbol equations. And the word equation is very, very limited. We know that sodium is reacting with oxygen and we know it's making sodium oxide, but we don't know any more. But the symbol equation actually tells us a huge amount. It tells us that there are 4 moles of Na reacting with 2 moles of O2. It's also highlighting the fact that oxygen is diatomic. And we know that as a result of it, we're making 2 moles of sodium oxide. And we know that sodium oxide comprises 2 sodiums and 1 oxygen. When we then go on to look at balancing equations, I've not put a huge amount on here. This is going to be fundamental to many, many aspects of what you do. So you need to be prepared to balance what might be very simple calculations, might be much more complicated. So in the first one, 2H2 plus O2 goes to 2H2O. Remember, you're just rearranging the atoms. There's nothing created or destroyed. On the second one, well, I can see my chlorines are unbalanced, so I need 2 LiCl, and as a result, I need 2 Li. My next one's slightly more complicated, but I've got 2 oxygens on the left, 3 on the right, so I'm going to go for the lowest common denominator of the 2, that's 6. So I need 3 O2, 2 Al, 2 O3, but as a result I'm now going to need 4 Al on the left. The final one is slightly more complicated. The key thing to remember here is whatever number is in front of CO must be the same number in front of CO2. And through trial and error, you might find that 2s don't work, it doesn't balance. But if we then put 3s in front, I can see that I've got 3C, 3C, I've got 6O, 6O. So all that's left for me to do is to balance the 2Fe. Now that's going to allow us to move on to the reacting masses calculation. This is a big part. It's a big part of the maths for year 12 and year 13. As you can see here, there is a worked example and you only draw the table out once, but then you fill it in the order that we have it. And I think if you learn this table, you are well on the way to being able to do any of the calculations that are thrown at you. There's one important thing that you need to consider, and that is this looks almost identical to the empirical formula table that we looked at in part 3 of this amount of substance video. The only difference here is that the mole ratio is not found by dividing by smallest, it's taken directly from the mole ratio in the equation. We'll see what that looks like in the range of examples that we're going to go through. But have a go at the question at the bottom. When you're ready, unpause and we'll take a look at the answer. So following through the steps, we have got the species we are interested in and the species we know about. So we've got the salicylic acid and the aspirin, and I've built my table. From there, I put in what I know. I've got 0.33 grams of aspirin. I can find its MR, it's 180. And when I've got both of those, I can calculate N, which comes out as 0.0018. My mole ratio is direct from the equation. 1 mole of salicylic acid makes 1 mole of aspirin. So I put that 1-to-1 ratio in. And if 1 mole makes 1 mole, 0.0018 moles makes 0.0018 moles. Now I've got the N, I can find the MR using the periodic table, it's 138, and once I've got that I can use my mole triangle or my mole equation and I find that my mass is 0.249 grams. Always remember to write that in the specified area within the exam question or write it separate from the table, 0.249 grams. Okay, let's take a look at another example. Unpause when you're ready. So, we have the equation, but it isn't balanced. I can see straight away that I have got 3 SO4s on the right. I've only got 1 on the left, so let's fix that one. I now have also got to deal with the fact that I've got 2 aluminiums on the right, so I need 2 on the left. And to finish off, I know that I need 6 H2O. Now, this is a slightly unusual question in the sense that you're being asked to do 2 reacting masses questions. I'm going to combine all of those into one table, but I will still do it as 2 separate calculations. So we're interested in the first instance, in B, about how much aluminium hydroxide we will make from a kilogram of aluminium sulfate. What you'll notice here is that I've converted that kilogram to 1,000 grams, just because grams is what we generally use. That is best practice. You're going to see examples later on where I'm perhaps not going to do that, but ideally you will. Now, once I've got that, I can find my MR for aluminium sulfate. Comes to 342.1. Once I've got my M and my MR, as always, I can calculate my N, 2.92. And I then need to put in my mole ratio. Now, we are interested in how much aluminium hydroxide is needed to make the aluminium sulfate. And I can see from the equation that 1 mole of aluminium sulfate would require 2 moles of aluminium hydroxide. At that point, I can start working up the column again. If the ratio is 1 to 2, then it's 2.92 to 5.85. Actually, with calculator rounding, it does come to 5.85 there. And I can then find the MR for aluminium hydroxide. And once I've got the N and the MR, I can calculate the mass, 456 grams. To work out the sulfuric acid, I'm going to do exactly the same thing with the left-hand column that you can see here. But in this table, I'm interested in the comparison to sulfuric acid. So 1 mole to 3 mole ratio, 1 to 3. I can then see that I've got 8.76 moles of sulfuric acid, and I can find its MR, which is 98.1, allowing me to get a mass of 859.4 grams of sulfuric acid. Moving on, let's have a go at this and unpause when you're ready. So here we've got an equation that we need to balance. We've got the sodium hydrogen carbonate breaking down to sodium carbonate, carbon dioxide and water. The balancing of it, I can see straight away the sodiums are unbalanced. And that's pretty much it. But the question did ask for state symbols as well. So solid, solid, gaseous and gaseous. It's important to note that the water does specify water vapour. At that point, I put in the 2 species I'm interested in to the table, and I build my MMRN ratio table below them. And I start to substitute in the data that we have. We had 10 grams of sodium hydrogen carbonate. We find its MR, which is 84. We then use M over MR to calculate N, 0.12, and we look at the mole ratio. The mole ratio of NaHCO3 to Na2CO3 is 2 to 1. So if it's 2 to 1, it's 0.12 to 0.06. I then find the MR of the sodium carbonate, in this case that's 106. I multiply my N and my MR together and I get a mass of 6.36 grams. Again, notice that that has gone outside the table as a very specific answer. What I'm hoping you're seeing here is that there is a very clear routine in the vast majority of these questions. Have a look at this question. See what you can do with the rest of it. I've started you off. And this is purely about reading all of the information. We've got 1,200 grams of carbon, 3% of that is sulfur, and we're interested in the sulfur burning. So 3% of 1,200 grams is 36. If I've got the mass of sulfur, I can work out the moles of sulfur because I can find its, in this case actually it's atomic mass, AR, but I get 1.121 grams. Now, if I then write the equation of S plus O2 goes to SO2, I can see that the mole ratio of S to SO2 is 1 to 1. So one mole of sulfur makes 1 mole of sulfur dioxide. 1.121 moles of sulfur makes 1.121 moles of sulfur dioxide. And if I've now got the moles and I want the mass, I find its MR, 64.1, multiply them together, and I get 71.89 grams. Another one for you to try. Unpause when you're ready. Okay, so we're starting with the symbol equation. And in this case, we have got AgNO3 plus KF goes to KNO3 plus AgF. They're all provided. And when you actually check the balancing, you see that that is already balanced. So we move on to part B. And we're using here not N is M over MR. We're using N equals CV. Because I've got a concentration of 0.2 moles and I've got a volume of 30 centimetres cubed. We're not going to leave it in centimetres cubed. We're going to divide by 1,000 because concentration is in moles per decimetre cubed. We need the volume to be in decimetre cubed. And that takes us to an answer of 0.006 moles of KF. Now from there, we need to look at the mole ratio in the equation. 1 mole of KF makes 1 mole of AgF. So my moles of AgF from that 1-to-1 ratio is 0.006 moles. That then allows us to move on to part C. We know how many moles there are and we know the volume. It's in 100 cm cubed. Remember to always convert volume to decimeters cubed. So I'm doing 100 over 1,000. When I do that, I get to a concentration of 0.06 mol dm to the minus 3. Here's another question for you to have a go at. Try, unpause, and then review. So in terms of the balancing of the equation, there's two ways to look at this. Everything is balanced apart from the oxygens. So what you could do is put a half in front of the O2. That would then mean that there were 6 on either side. The alternative is that you multiply all of the others up. I've done this by balancing my sulfurs. I need those to be the same. I also need to bring my calcium up, and I can see that I need 2 CO2 as well. Then I got on to the actual calculation. We're going back to the table method here. So let's consider what we know and what we want to know. I've got SO2 and CaSO4. So let's put those into our table that hopefully we're very familiar with. Now we've got 500 tonnes of sulfur dioxide. You'll notice I've left it as tonnes. Converting tonnes into grams is going to leave us with a big unwieldy number. So let's leave it as tonnes because our answer will then come out as tonnes. My MR is 64.1, taking me to a mole value, M over MR, of 7.8. My mole ratio from the equation is 2 to 2. So if 2 moles makes 2 moles, 7.8 makes 7.8. I can then find my MR, 136.2, multiply those together, and I get a mass of 1062.36 tonnes. Let's move on to another example. We've got here glucose breaking down to ethanol and carbon dioxide. Unpause when you're ready and let's look at the answers. So we identify what we know and what we want to know. In this case, glucose and ethanol. We put those into the table, as always, and then we start to substitute the figures in. I am converting kilograms to grams. We've got 5,000 of them. We're going to divide that by the MR, which is 46 for ethanol, taking us to 108.7. The equation tells us that 1 mole of glucose makes 2 moles of ethanol, so my mole ratio is 1 to 2. And that means I can take that ratio through to the number of moles, and it's going to be 54.35 moles of glucose. I can find the MR of glucose, that comes to 180. I multiply the 180 and the 54.35, and I get a mass of 9782.61 grams. Now we're not done because we've got a chance here to revisit our ideal gas equation. And I'm going to put down what I would always do. Here's my pressure, my volume, my N, my R, my T. I've filled in as much as I can. I'm going to convert the units to the ones that I need to convert the units to. We're still missing N. How many moles of carbon dioxide? Well, it goes back to this table. There's no calculation to do it because for every mole of ethanol that I make the same number of moles of carbon dioxide. It's a 2 to 2 ratio. So my moles of ethanol, 108.7, is also my moles of carbon dioxide. Once I've got all of those figures, I can put them into the rearranged equation. V is nRT over P. I substitute those figures in, I carry out the calculation, and I get to a volume of 2.69 metres cubed. That takes us to the end of part 4 of this video walkthrough. Thank you for listening.